NAD might have been one of those molecules that existed before life itself that then enabled life to happen.
Dr. Dan Pardi, welcome to the podcast.
Thank you so much for having me, Nick. I'm really delighted to be on your show.
Yeah, me too. So right here, I have a bottle that you might recognize, the listeners will not, and the visual watchers may not as well. I'm going to take 2 of these capsules. What is it that I'm taking right now?
Oh, watch out, audience. So this is Qualia Life Sciences NAD plus product, and I am a big fan. So hopefully this is going to power an incredibly awesome podcast.
Sweet. So
I took it myself today.
Oh, did you?
Mm-hmm.
Break down, what exactly is it? You mentioned NAD plus. Talk to me about what that is.
Yeah. Yes. So it stands for nicotinamide adenine dinucleotide. That's its name. And it is a universal coenzyme that is in all living cells. And, you know, as scientists, it's easy to use some of these terms because we're familiar with them. And in fact, Daniel Kahneman calls this the curse of knowledge, where you throw around terms that are familiar in your area of expertise as though everybody else was working in that space. Lawyers do it, you doctors, everybody does that. But since this interesting molecule is a coenzyme, why don't we take a second and describe what that is? And an easy way for me to remember, to like really process this is, you know, think of like enzymes as a machine in like a workshop that is making a product, okay? And a coenzyme is like a tool that the machine needs to do its job, right? So it's assisting in how it's assisting the machine to do its work. It's usually organic, so carbon-based, and it's often from different vitamins. And one example is NAD, which carries electrons like a wrench turning bolts. Think of it that way. All right. And I'll mention this too, because it might also come up, but then a cofactor. So you have coenzymes and cofactors, and cofactors are like a part or an attachment. So think of it like these are usually like inorganic, like a metal ion, like magnesium, and they help to stabilize the machine's moving parts. So, you know, think of it like a bolt that the machine needs in order to operate. So that's a really good analogy to understand. You've got enzymes that are machines, you've got coenzymes that are tools, and you've got cofactors, which are, you know, parts that the machine needs to do their job in order to work. And there are 4 coenzymes really when we're talking about NAD that we really care about. As Charles Brenner, a name that I know you're familiar with, he's a scientific leader in this space, and he calls them the crown jewels of metabolism. And you know, remember, metabolism isn't just like glucose regulation. It's the sum of all chemical reactions in the body that convert food, energy into and building, so converts, food into energy and building blocks, and also eliminates waste. So it's like the building up, it's like taking food, making energy, building up tissues in the body, and also breaking things down and getting rid of them. That's metabolism, and these are involved in every single process in the body. So that's what we're talking about.
Okay.
Yeah. And I'll say a little bit more, because this is actually a critical part too, if you don't mind. That so we have NAD plus and NADH, and think of it like a battery. And the battery, so NAD is an empty battery, and that doesn't sound good because we want full batteries. But what an empty battery can do, think of it more like a rechargeable battery, right? An empty battery can go around and pick up energy or electrons from a reaction, and they can bring them around the cell. And then NADH is a charged battery, and that carries the electrons and then delivers them to another machine. So you can see that really when we're talking about NAD+, we're really talking about this battery system that's moving around energy. And then, of course, there's NADP and NADPH. I won't go too much into that just because it's probably overkill, but they just do specific jobs that are for building and repair. But that is what we're talking about with NAD. Coenzymes that act like batteries and move electrons around cells and power all of metabolism.
Yeah, and so the real importance there is that by transferring energy throughout the body. You're powering all the different organ systems, the processes that need to occur, not only for life to exist, but also to support higher order operations and the things that we all want to do to age more gracefully, to think more sharply, that type of stuff as well.
Yes. Think of it as the performance of the body and all the cells that they have jobs to do. And without NAD and NAD plus, they can't do them.
Why, if this is so fundamental, did it largely fly under the public's radar until around 2017 with Dr. David Sinclair's book, Lifespan?
Yeah. So, of course, people in the space got to know this molecule earlier, but it gained popularity with that book because that became one of the most popular health books of all time. But if you don't mind, I think that the story that is even more interesting if you go back way, way back in time, like much, much earlier than 2017. In fact, really back to the beginning of when like the Earth formed. That's how far back we're going to go.
Let's do it.
Okay. So as you know, the Earth formed 4.5 billion years ago. And at first the surface was just this molten, think of it like molten lava, almost like a sun. That's what the Earth looked like. And then about 100 million years later, the crust started to form. So it cooled, the crust started to form, and you started to see the beginning of oceans. And the way that those oceans formed is that volcanoes that would erupt from the crust would release vapor, and then those would condense into oceans. And there's some possibility that some of the water was also added by icy comets that hit the Earth. So very inhospitable environment at the time. And the atmosphere of the Earth at that time looks nothing like it does today. So it was methane, ammonium, some water gas, and a lot of hydrogen. And so how did life even begin at all? And so there's a really cool story from the 50s where there's two researchers. It's called the Miller-Urey experiment. It was from 1952. So Stanley Miller and Harold Urey at the University of Chicago. What they did is they simulated early Earth conditions, and they in their lab, they created a chamber that had the same atmospheric conditions they think as the beginning of Earth. And what they did is they added electrical sparks into that environment. And and those sparks were actually meant to simulate lightning. And within a week, only 1 week, you saw that just those conditions alone, you saw the formation of amino acids, right? Providing like the natural chemistry that could possibly create the precursors to life, right? So these organic molecules could form proteins and nucleic acids, and they were really basically setting the stage for life to begin. And this whole field is called prebiotic chemistry. So now typically when we think of prebiotics, we think of like fibers and phytonutrients that we consume that go and feed the microbiota. But if you biotic means life. So this was the necessary instrumental chemistry that enabled life to happen. And the reason I'm mentioning all this is because it's thought that NAD might have been one of those molecules that existed before life itself that then enabled life to happen. And that's why, to me, this is one of the most interesting stories, actually, because it was, as we know, these redox reactions that we discussed already, this was something that could enable them to occur. And so when you had the earliest formations of membranes, these reactions could take place inside, and somehow this is the beginning of life. In fact, this goes back before something called LUCA, right? The last universal common ancestor. And this isn't the very first organism, LUCA, but it's the cell. Every single organism that's alive today has cells from LUCA. They're made up of those types of cells. And so, yeah, that's what is, I think, a really fascinating part of this whole story is that it was probably something that enabled life in the first place.
Mm-hmm. So if it enabled life in the first place, you'd expect to see like that, those mechanisms and the presence of that molecule conserved across species. And you'd also expect that if you didn't have any of it or enough of it, that might interfere with life in general. Are both of those true?
Yes, both of those are absolutely true. That this is a fundamental molecule that was uh, the whatever force you want to call it, life itself was figured out and instrumental very early in the process, and now is enabling uh, organisms to live that we see in all species across the planet. And so it is a very foundational molecule to life itself. Now,
If it's
yeah,
so
yeah. Go ahead.
if it's so foundational, why did it take us billions of years to discover it?
Yeah, so that's a really uh, cool story too. Is just thinking about, if you want to call them like scientific historians that go back and look at the how did life itself, like what are the different epochs of human life? Like sometimes you hear people talk about the evolution of humans, that humans began 200,000 years ago in the same form that we are today. That's not true. Humans, we are a direct lineage from the very first cells that were able to continue to live. And so there are four major epochs of human design. And the first one was cells figuring out how to become maximally efficient. And that process took 3 billion years, 66% of the time of Earth's life, just figuring out how cells could become incredibly efficient. So they had the same foundational molecules like DNA. They did redox reactions. And in that period of time, you had what's called the great symbiotic event, endosymbiotic event. And that is where a bacteria inhabited another single cell, and there was a division of labor. And that division of labor, what those little proteobacteria are, what we know them as is mitochondria. But that division of labor meant that the primary cell that ingested those bacteria became the house for the nucleus and all the genetic material. And the mitochondria then enabled all of the energy production for the most part. And when that happened, it allowed a billion-fold increase in the size of cells. So think about how tiny cells were, and they become much, much bigger. And the amount of energy that every gene now had available to it was 1,000-fold increase. So what do you think happened there? More genes were enabled to be built into our genome, and that enabled the ability to create more complicated for organisms. So then the second major epoch then was multicellularity. So cells came together, and not only did they kind of turn into this fleet where they were sending signals back and forth to each other, but eventually there was specialization. And so cells could now say, all right, we're going to have a division of labor, kind of like I just described in the cell, but now is amongst the fleet of cells. And so some cells could be doing some activities, others could be doing something different, and that became, again, more efficient. And what each major increase that occurred, what it enabled is for these organisms to be better at procuring resources in their environment, which created a survival advantage. And pretty soon, those organisms that had these newfangled features were going to outsurvive organisms that didn't. So think NAD is powering the very simplest reactions, but what it's enabling now is for this increase in complexity. So now what you have is cells that are turning into different tissues. You have neuron cells, muscle cells, all sorts of different types of cells. And eventually then that led to this organisms that had bilateral symmetry in a brain. So there was orientation. It wasn't just this group of cells. They actually had structure. And this bilateral symmetry was important. So these simple little roundworms that now could go and navigate, the brain could say, we are detecting some important signals over here. It could be food, or it could be a predator. We're going to move away from the predator. We're going to move towards food. And the brain could orchestrate that movement in the right direction. Again, better survival advantage. So then, and then that led all the way up to massive dinosaurs. The life just kept building and building until you got these huge, massive structures. And then eventually the next epoch was mammals. And so mammals were, the major two features that they had was endothermy. They could generate their own heat, which then enabled them to be able to survive in an environmental context with a wider temperature range. because they could make their own heat, right? And they could sweat. Now think about poikilotherms, which don't do that. They have to be out when the sun is shining, and then they have to try to protect their heat source at night, right? So that limits the amount of a 24-hour period where you can go find food, right? Endotherms could basically hunt or get resources 24 hours a day if they wanted. Yeah. And the other major mammal advantage was lactation. So think if resources were sparse, you might not actually be able to go find, if you're not finding food reliably, then the very weak young could die. And so you would have to then have a different type of reproduction strategy where you make hundreds, tens to hundreds of babies, hoping that some will survive. And what lactation enabled is that there was more investment into fewer offspring. And so let's say there's like 2-week period where the tribe can't find food. Well, lactation is going to enable stability of nutrient supply, which is going to help the vulnerable offspring survive. And those were the two major advantages then that were conferred during that third epoch. And then, the fourth epoch is us as humans. And what is really magical about us is that we have an incredible ability to specialize as individuals and amongst the tribe. So when you're born, think of language. We have the propensity to learn language, but the language you learn is conditional to where you live. So yes, you specialize to a specific language based off of where you're from. Now, in a tribe, you have people that might be hunting or gathering. You have better verbal communicators. You have medicine people. And what this does is it confers resilience amongst a group of people. So those are like the four major epochs. And it's all kind of starting from this optimal design of cells. And so that's, the question, I think it's probably like the longest answer to like a simple question, which is like, why did it take so long? But the unique and inimitable capacity of humans, and like some of the things that we were able to do, which then enabled us to have science, is we were able to offload certain skills into the environment. So we developed writing. We were able to then get clothing. So clothing added another layer of thermal protection, extending our own ability to thermoregulate as endotherms. We were able to use symbology and writing that enabled us to preserve memories. So you wouldn't have to just hear stories, but you could build sequentially on top of the learnings of prior generations. And, think of like an exponential curve, right? It starts really slow with like a minimal change from generation to generation, and then all of a sudden it takes off. And it is a bidirectional relationship. So the more that we learned, the more we had to learn, which drove evolutionary pressure for brains to expand. You meet that with resources availability. So now we have better, also with fire. Fire also enabled us to eat food sources that we couldn't eat previously, like starchy potatoes that were mostly cellulose. So the fire could break down that energy. And now we had an expanded resource of food. All of those conditions led to the point where now, let's say a couple of 100 years ago, we now have a more of a scientific method where our knowledge isn't just, hey, what do you think about these ideas? I've got some colorful stories to tell you about what's happening, to actual proof that these important things are taking place. And so it was right around like 1906, obviously, so NAD's been around since the dawn of life, but we really stumbled on it like a century ago. And so the scientific method had been well established at that point. And this first discovery, like many others, was serendipitous. So there was a researcher named Arthur Harding. He was studying fermentation in yeast, and he found this mysterious coenzyme that made sugar break down faster. And he didn't know what it was. But what he was basically looking at NAD, and what he later on in 1929, he ended up winning the Nobel Prize for this exact work. So that was the beginning. And then if you look over that last century, in the 30s and 40s, we figured out the structure, and we figured out that it was like there was a vitamin connection. So that was important to then finally understand. Like, we kind of understood what was happening with NAD, but we didn't know what it looked like. And so he showed that NAD was some researchers that showed what it was, a dinucleotide, so linking two nucleotide molecules. And as a reminder, nucleotides not only carry energy, but they're also the basic building blocks of DNA and RNA, right? And so then in the 50s, we figured out that it was this a hydrogen carrier in redox reactions, thanks to Otto Warburg. And so, yep. And then going beyond redox in like the 60s and 70s, we discovered it wasn't just shuttling electrons, but it was also used as a substrate. So now for things like PARPs and DNA repair, stuff that we might talk about a little bit later, but we found that it had an expanded role. And then in the 80s and 90s, that's where really the sirtuin era began. So this is work by Lenny Guarente, he did his work at Harvard and then eventually at MIT, but this was the first book that I read. It's called The Ageless in Aging. So it was published in 2003. I don't remember how I discovered it, but this book is filled with highlights, and it was their work. What at the time is that the idea of studying of aging itself was not favorable to research departments. It seemed like pseudoscience. And so people who were working in aging at that time were very brave. And so what they figured out is that, there seemed to be, through their work, this connection between NAD and longevity. And then in the early 2000s, this is when you see people like David Sinclair, who was a part of Lenny Guarente's lab at MIT. He started to expand. They felt that sirtuins were really critical to the aging process. And in fact, in 2004, Charles Brenner, as you know, he published in the journal Cell that there was this other molecule, nicotinamide riboside, and this was a new NAD precursor. So you had this connection between NAD and sirtuins, and this sort of helped to spark this supplement field with Elysium and, Chromadex and other compounds. So you could see the story was building, right? From fermentation to structural development to understanding its various roles like redox and also in, as a substrate. And then it really began to take off because aging science became a thing. So this is a story that had been developing for a couple of decades now, and a space that is now credible, and a lot of excitement is going into it. And the whole geroscience space is essentially saying, can we manipulate the mechanics of the aging process in a way that offers better health span and possibly even extends maximal lifespan? And so there was this NAD plus renaissance as like the first darling of this burgeoning space. And that is why it took so long, right? We had to build all the foundational human abilities. We had to clumsily stumble into the fact that this was working in some way. And then decade by decade, we built on top of that knowledge. And now most people feel like this is something that has some serious potential to help us age differently. And that's why it's so interesting.
Yeah. So you mentioned a lot of things there. The different places we'll come back to, including like the sirtuins. That's an important part of the conversation and relevant to it as well. Before we explore that area, if you were to look at, say, an aging organism or a human, you would probably see other deficiencies that are common, perhaps more like individually than as a collective, perhaps as a collective as well. How do you know it's not other cofactors or other coenzymes that would produce the same or better effects than administering simply NAD or NAD precursors?
It's a very sophisticated question, because why not talk about flavins? Flavins also are implicated as possibly like riboflavin. These also act as coenzymes and are necessary in fueling various energetic reactions like the Krebs cycle and TCA and electron transport chain. So they're involved also. Why aren't they the protagonist in this story? Well, in that case, for example, the flavins are limited in terms of what they do. And so not only is NAD sort of central to a lot of these metabolic processes, but because it's also connected with things like DNA repair and sirtuin maintenance, these other things that we do care about, and is more ubiquitous with also more fluctuations, not only within a 24-hour cycle, but also across decades. You actually have a more interesting story as kind of fingering this molecule as being more important than just other molecules that in moments do something similar.
Okay. And then what do you see? I've seen and read different things over the last, I want to say 7 or 8 years about the decline curve of NAD over lifespan. Originally I saw that by age 40, like we had lost already a huge chunk of it. And now I saw something that was revised more recently that perhaps we don't lose quite as much as like the curve isn't quite what they initially thought. What is like the latest research saying around like the decline of NAD throughout the human lifespan?
So let's look at the number of molecules in a cell. So we get a grasp when we're thinking about declines over time. So in a typical human cell, there's probably, roughly 100 to 500 million molecules of NAD. That's a lot, right? And then each molecule, each one is participating in 1,000 to 2,000 redox reactions per day. So when you combine those numbers and you think that every human cell experiences 2 billion NAD redox reactions per day. And it gets staggering when we think about the body having 37 trillion cells. And so the total number of NAD reactions in the body is like 10,000 times greater than all the stars in the observable universe. That's amazing. All right. So there's a lot of reactions that are happening for us. And by the way, just so you know, it's not uniform where NAD is. That the mitochondria has like 60 to 7% of our stores. You see these intercellular compartments maintain not only different amounts of the total pool, but also different ratios depending on their job. The ratio of NAD to NADH, and so when we talk about these things like levels declining, how reflective is that of overall, like some pools actually being maintained where others are being depleted? It is sufficiently complex. But yeah, I mean, maybe 30% is in the cytosol, and in the cytosol, you are maintaining a extraordinarily high ratio. So like 700 to 1 of NAD plus, which means that it's ready to go around and grab free electrons and then deliver them to another enzyme. Where in the mitochondria, that ratio is not quite as much. But yeah, so we have different levels in cellular compartments. We have different ratios. That is a more true picture of what the reality is. Now, having said that, yes, you're right. Levels do decline. So you'll see, for example, in your 20s, let's say if 20s are, your standard of 100%, so how does it decline from that level? And yes, we do have different amounts based off of like when we're developing, because that's a very energy intensive process. But if you say, 20% is your peak, and then you're going to, you're almost losing 20% every decade. So 80% of that in your 30s, 60% of what you have in your 20s by your 40s. And the one that's easiest to remember is by the time you're 50, you've got about 50% of what you had in your 20s. So that's a good way to think of it. Now, your question also asked, are those numbers real? Well, we know that depending on how you live can definitely affect how much energy your body is making. So there is a decline. We can't avoid that, but we can affect it. And we can affect it by making smart choices about about how we spend our 24-hour period. And, considering all of that, I'm still favorable that supplementing with this as a, sort of a geroscientific gives you like this geroscientific advantage, right? So on top of doing a lot of the things that are either going to provide the signals that may help your body make more NAD or limit the ways that it is consumed more aggressively as we get older, you can actually maintain much more youthful levels. And you can see that in people who live really healthy compared to those who don't. I mean, it's not, of course, just NAD, but it is, what I'm saying is that you can definitely see differences in terms of how people live, in terms of what they look like and their energy levels that they manifest in their life.
Yeah. What are some of the causes of premature NAD decline?
Yeah. So premature. What I would say is that the premature acceleration of decrement of NAD levels has to do with really a loss of homeostasis in terms of like the balance that the body's trying to maintain. And so, yeah, think of it in two ways: less production and faster destruction. So you commonly are going to hear things like, CD38 PARP sirtuins. I've mentioned those already. I'll just start with sirtuins because that's sort of where the story started in a way. But, these are, they've been referred to, sirtuins, as guardians of the genome, even though that nickname doesn't really capture everything that they do. But this is a family of 7 proteins numbered SIRT1 through SIRT7, and they work as enzymes that strip acetyl groups from proteins. And every time that they do this, they use NAD. So, where do they operate? The different sirtuins work in different compartments. So the nucleus, like regulating DNA, others are in the cytoplasm that are helping to support cell cycle. And then others are in the mitochondria that are sort of fine-tuning how we make energy. But when active, so when these sirtuins are active that need NAD, they're going to be boosting NAD repair. They're going to cut down on inflammation. But they help to stretch resources that help cells survive under stress. So they're doing a lot of important things. And the reasons that they're often tied into aging and longevity is because like I said, they're consuming NAD. So I want to actually point this out. So earlier we talked about these redox reactions. And again, think of those as shuttling electrons for, it's like moving energy in a cell to enable processes. That's a fundamental use of NAD. But a substrate, they can also be used as substrate, which means that the molecule itself is broken down. And if you remember, a substrate can be different things depending on whether it's a catabolic reaction or an anabolic reaction. So like, let's say, in a catabolic reaction, glucose is the substrate for glycolysis, right? Glycolysis is the breaking down of glucose. And in an anabolic process, it's like, think of it like in the first step as a fuel. And in the second step, it's a building block. So that's what, and NAD can basically serve as both, right? It's a substrate for these types of reactions. And when, if sirtuins are running hot because they've got a lot of repair, or there's imbalances in energy production in the mitochondria, they're just going to churn through NAD faster. And so you now tie together all of these other hallmarks of aging: diminished, NAD efficiency, less mitophagy, which is the intercellular quality control of mitochondria. Now your body is less efficient at making energy, which then is going to be tied to because of that, you have increased propensity for inflammation. You have less energy for DNA repair. And I'll say this: every cell, the human genome is undergoing a massive amount of DNA damage per day. So there's over 1 million DNA breaks per cell per day in the human genome. That's a lot of repair. And we get less efficient at that as we get older because there's more repair that needs to happen. And we also have this conspiratorial, or this conspiring influence, not conspiratorial, but conspiring influence of less energy production. So it's like more damage and less energy to fix it, right? And so, yeah, aging is seemingly inevitable. I mean, we are working hard to try to figure out if we can solve that. But at the moment, it is fair to describe it as you are going to experience aging. And that's a really interesting conversation too, and probably another hour podcast. Like, what is really the ultimate driver of aging? Is it these hallmarks, or are those hallmarks that we talk about really just proximal examples of the aging process at play? Which I think that's the truth. So we have these, sirtuins, they're playing an important role. And there's actually to kind of extend this story that we were talking about earlier when I talked about Lenny Guarenti's book. So David Sinclair was really emphasizing that sirtuin 2 extended lifespan under calorie restriction. And so based off of that idea, he ended up, he determined them these longevity enzymes. He thought that this is what is actually controlling.
And sirtuin 2 refers to one of the sirtuins in the family of sirtuins.
That's right, one of the 7. Yeah. So then in 2004, he ended up him and a few others founded a company called Sirtris. So sirtuin, Sirtris. And they used activators like resveratrol and tried to turn these into anti-aging drugs. So after the company went public, they were then acquired by GlaxoSmithKline for $720 million. And within a few years, that program totally fizzled. So by 2013, Sirtris was completely shut down. And so, not everybody bought the hype at the time. In fact, as I mentioned to him earlier, Charles Brenner argued that sirtuins are, a part of the story, but it's been majorly overstated. Like, yeah, they're doing important things, but he feels that NAD is actually the more interesting story than sirtuins. And so he thinks that's the real driver of metabolism, not just their ability to activate sirtuins. So anyway, the consensus now is a little bit more balanced, that sirtuins are definitely important. They do an important role, DNA repair, they help with metabolism, but they're not these master regulators of lifespan as Sinclair and Guarenti once imagined. They're part of a...
Yeah, I was going to ask you about that because I saw that you included the famous, or I guess you could call it these days, more infamous resveratrol in your ingredient formulation. And I was curious, obviously it has to do with sirtuins, but there's both camps where it's we get sirtuin activation is important to complement increasing NAD levels and NAD function. But then again, there's also a lot of the research that could not be replicated and is not replicated, at least in humans, around resveratrol specifically. And I've seen some about potential undesirable effects from high doses of resveratrol and other sirtuin activators. But then again, it's they're also not very well absorbed. That's another downfall of them. So I'm curious what your rationale was. It sounds like for some level of sirtuin activity.
Yeah. So you're right. So the problem with resveratrol is it has a hard time being absorbed. So that's a major limitation to sirtuins, to resveratrol. It's still an interesting compound. I mean, because it had the advantage of calling it a popular molecule at the time, it was able to generate a lot of research for a little while. And sometimes, a lot of things in sciences or with any news story, there's a pendulum swing. So you have overemphasis, exaggeration, hyperbole about what something can do. And by the way, I've seen this just a million times, and I'm sure you have as well. And then you have people that have been pushing back so hard that they might end up pushing back maybe harder than what is reality. So there is some evidence that resveratrol can activate SIRT1, and that is present in humans. So where SIRT2 is mostly in yeast. And so what's interesting to us is that it upregulates a really important enzyme that we do care about. And that enzyme is one that is involved in the salvage pathway, which we haven't discussed yet, but there's basically the salvage pathway is the major pathway of NAD synthesis. And just so I don't go off on too much of a tangent, because we can come back there. So NAMPT is nicotinamide phosphoribosyltransferase. That is an enzyme that is the rate-limiting enzyme of the NAD salvage pathway. So what that's doing is it's helping to take nicotinamide and depending on the process, a multi-step process to resynthesize NAD levels. Okay. And so what was interesting to us is that the inclusion of it has the ability to kind of activate this enzyme that, again, is rate limiting for resynthesis of NAD. That's why we included it. Whenever you have a formulation, you cannot determine what, well, you could. It would just be probably impractical. Like you could recreate your formulation 10 different ways, removing one of the elements each time, and then going back and doing the clinical work to see if the magnitude of impact is equal or greater or less, than what you'd see versus, let's say, your standard formulation. That'd be great. Yeah, it would be great if we had that information. We could maybe create the optimally efficient design. Maybe with AI, we could do that. But right now, the way that you create a formulation, I would say I don't want to say guesswork, but you use science and you put together what you think is going to make the most sense. And we thought that including resveratrol was a low risk addition that had some potential upside.
Okay. And then I don't know if you know Dr. Sandy Kaufman, but she likes pterostilbene over resveratrol. And you guys settled on resveratrol, I'm guessing because there's a lot more research than there is on pterostilbene.
There's a good amount of research on pterostilbene. And so yeah, that is a stilbene. It's a metabolite of resveratrol. It's thought to be, better absorbed. Of course, so if you look at Elysium's product, it's pterostilbene and NAD precursors. But yeah, so there is a lot of evidence for, there's more evidence in trans resveratrol. So I'm still optimistic that the inclusion of this molecule was something that's benefiting the end user. But yeah, you could also argue for the inclusion of that metabolite of resveratrol, the pterostilbene too.
I'll go back to where we were previously, because I think giving people like some concrete ideas of what it is that's lowering NAD levels can help like understand, like paint a picture for like what to, I guess, minimize. And you mentioned a couple things as being like big consumers of either NAD or I guess activating processes that consume NAD. And one of those is inflammation. So it's like if you do things that are inflammatory, you're going to be capping your NAD levels. And also if you damage your DNA more than you otherwise would, whether it's from things that are great in reasonable levels, such as sun exposure, but if you're spending 12 hours a day under direct sunlight in certain parts of the world, that might be doing more harm than good. And of course, there's a lot of other things that do DNA damage as well. That's just like one of the more natural ones that can be healthy when dosed appropriately.
Yeah, yeah. You're absolutely right. And there was a very interesting study from the New England Journal of Medicine, as prestigious of a journal as there is, looking at nicotinamide in 1,000 milligrams and in people that were at high risk for skin cancer. And what they found is that there was lower risk of that over a year period. It's a pretty high dose of nicotinamide, but that's what that study showed in a very prestigious journal. And you're right. So I've given a talk on sun exposure. I'm very interested in light and all the effects that light have on our health. And the issue, so sun, of course, is a hormetic stressor. And like any sort of stress, we have a certain stress tolerance that we acclimate to in the environments that we spend the most time in. So you have people that get a lot more sun exposure that don't have it's not linear where they have massive, risks of skin cancer. But to be fair and to be accurate here, skin cancer is the #1 cancer in the world. And one of the reasons why is that sun exposure, the actual UVB rays will cause these pyrimidine dimers. They basically they cause breaks in your DNA. So as I talked about earlier, there's over 1 million different molecular lesions that accumulate per cell per day. That's a lot of DNA damage. And that's not a fixed number. As you said, if you go out and you're doing things that are going to cause more DNA damage breaks, like getting a lot of sun, particularly more than what your body is used to. So imagine, you've been inside all winter and then you go on a spring holiday and all of a sudden you're sitting outside and getting way more sun than you were used to. your body is going to have a harder time dealing with that. So not when you get more sun, you are also upregulating your DNA damage response, which makes total sense, right? It's now been primed through lower levels of exposure. And so, sunshine ends up being just like any other health factor in our lives. It requires discipline.
I don't want to pick on sunlight here because I don't want people to hear this and then all of a sudden be extra scared of the sun. There's already plenty of that in the world. And I think the sun has incredibly beneficial overall net effect when used responsibly at the amount that your particular skin can handle. But there's also a lot of other things that cause like DNA damage, such as like X-ray or gamma radiation, like different radiations, and then like perhaps exposure to certain chemicals. Like those are things that have very little hormetic benefit, and they probably have a much larger impact on NAD levels and like causing more DNA breaks, I guess. And so it's like those things perhaps focus on reducing or eliminating as much of them as possible. And then you can look at the other things that are also healthy. Like if you're not getting any sun, don't use this as justification to like totally continue avoiding it for the rest of your life.
That was the concluding message of the talk that I gave at the Ancestral Health Symposium. I don't remember what, maybe 2019. In fact, if you look at other, you getting sun exposure also lowers the risk of other cancers that are also quite deadly, like colon cancer and lymphomas. So obviously we evolved on a planet with sun exposure for part of the day. So our bodies do know how to deal with it, but it is our binge purge relationship with sunshine that can be problematic. So like what you just recommended, because I agree, sun exposure has clear and definite health benefits. The discipline is involved in not getting too much at any one time. And so you might have to get an unsatisfactory amount when you're going out for the first time in a while. And that is the hard part. You get all ready, you put your bathing suit on, you go sit outside, and you're outside for 5 minutes. And, and you're like, well, it feels good. I want to stay here longer and read my article or listen to this podcast. And that's the hard part about it. In fact, exercise is a hard part, is the effort you have to put in. And this is the discipline to just only get a certain amount, even though it feels good and you want to get more. So that's I'll just conclude with that on sunshine. But you're right. There's other factors, of course, too, that are going to drive, DNA damage. And I should say this too, that the million molecular lesions per cell per day is a part of normal cell metabolism. That is just a consequence of living. It's not because we're doing anything wrong. So it's important to say, but yeah, you were asking about inflammation, and that is a key one.
Well, are those the big factors, like reducing inflammation, minimizing like unnecessary DNA breaks, anything else that are like the big overarching categories to focus on?
Those two. So doing what you can to lower inflammation. The way that I think of inflammation is, as follows, that inflammation is kind of thought of as a dirty word. And what we're really talking about is excess inflammation or chronic low-grade inflammation. That's really where the problem is. Inflammation plays a very important signaling role in the body. So what we want is inflammatory homeostasis, right? We want our body to have really effective, very sensitive inflammatory signaling. And as we get older, that due to a massive confluence of factors, our ability to regulate that balance of inflammatory signaling diminishes. And as a result, we have things like, CD38, which is this cluster of differentiation 38. It's a membrane-bound glycoprotein, and it functions as an extracellular NAD hydrolase. So what that's doing is it's consuming NAD for the purposes. So it's doing a variety of things: calcium signaling, immune cell activation. So these receptors are expressed on lymphocytes or white blood cells, and it helps to regulate their proliferation and function. So it's doing these really important work in our immune system. But the more active our immune system is, like during states of chronic inflammation, you're going to be over-consuming NAD. So that's the inflammatory angle. And then the PARP angle is these enzymes that are actively fixing NAD repair. So when we have more when we have more DNA repair than is needed, then the need for NAD is going to go up. So now you've got those are a couple of different factors. There's also, it can be, as I mentioned earlier, another use of it is that NAD can be phosphorylated into NADP, and that's important for building up and maintaining stress systems. But it is another use of it. So you have inflammation dragging you down. You've got DNA repair dragging you down. You have normal uses in phosphorylating NAD. So yeah, that's, it's doing a lot of things, and there's just some factors of aging that are a part of living that mean that there's more of a drag on how much NAD is available.
Gotcha. Okay. And when less NAD is available or those other factors start to get higher, what are the things that people notice as like symptoms of that issue?
Well, you could attribute every symptom, consequence, phenotype of aging to energy, right? Because it's involved in all of it. And that's kind of an unsatisfactory answer. But what might a person experience? Well, you're going to see graying of hair, wrinkling of skin. You might have less sharp mind in some ways, less sharp working memory. You would feel fatigued. The thing that I noticed when I started to take our product, which really was motivating for me personally, is that I have always recovered slowly, relatively slowly from exercise. I've been a lifelong athlete. I care about it, but I feel like it takes me an extra day to feel really fully recovered compared to my age-matched counterparts. And it's always been a source of frustration. And so what I pay attention to it. I employ a variety of strategies to try to recover faster, of course, focusing on sleep, maintaining circadian rhythms. Those are really important. I do daily stretching. But, I just can't maintain a pace. Now that I'm 51, I can't maintain a pace that I did when I was younger. But what I noticed is that I was recovering faster when I started to take it. And that's hard to fake because I have probably like 5 years of data where, I'm trying to do yoga multiple times a week. And I'm like, you know what? I'm just not really feeling recovered to do it again. And I could squeeze more yoga sessions into my week and feel good, not feel like depleted and strained. That was, I think, the single most impactful personal experience. But, individual mileage may vary, right? So we all age in very unique ways. I mean, there's obviously connections and overlap between how we age, like graying hair, wrinkling skin and graying hair, but we all kind of do it in our own unique way. And so somebody might notice an improvement in a symptom that I don't notice at all or don't currently experience, and have no benefit on how they recover. So you have to assess yourself. And there are those who pay very close attention and would know when something is happening. And there are those that don't quite understand their body very well. They don't listen to it really, they don't pay super close attention. So you also have different, phenotypes of observers in the equation too. But yeah, those are things that a person might experience. Now from the clinical literature, you actually now can use science to say, okay, what have we learned? And the first major studies in this were looking a lot at cardiovascular health, still the number one killer in the United States, although we've made improvements there. And so they were mostly looking at the flexibility of vessels. So as you get older, your vessels will become stiff and rigid. And that means that they have less of it. They're less good at delivering blood flow throughout the body. And it also promotes the silent killer of blood pressure. So when they become stiff, then you're more likely to get blood pressure because they don't have as much laxity to ebb and flow, to dilate and constrict. And so that was one of the first benefits that we saw, that there was significant improvement in, basically it looked like people who were taking this over various stretches of time, usually somewhere around, 8 to 12 weeks, those people were experiencing benefits that could be observed in the various ways that blood vessel health was measured. So they looked younger. And that was pretty darn exciting. Some work in brain showed improvements in working memory. Um, you could actually see some localization in some areas of the brain, so it did look like it was getting in there. And I think that there's a lot more research that needs to be done looking at the brain. And there's even some formulas that could be exciting, like intranasal or ways that might bypass the blood-brain barrier. There's more work to be done there. We talked about skin. We now see topical applications, so being able to then put it in a cream, put it directly onto the skin, having it act transdermally to get into the dermocytes and create new. You see like increase in collagenation, you see decreased wrinkling over a period of time. So yeah, there are signs that it's working, and that's cool.
Yeah, it is. And then also, like, there are multiple different precursors and like types of like ways of increasing NAD levels. Like you've mentioned NAD plus a bunch of times so far today, and you can't, as far as I understand, just take oral NAD plus supplements because of the molecule size and its inability to enter cells effectively. So people take precursors to NAD. What are your thoughts there? Obviously, you guys chose a particular one. There was a paper that came out, I think it was earlier this year, called NAD World 3.0, and that's showing that a certain form has special transporters in the gut, but like a lot of this science is still unfolding. What made you guys settle on using a precursor? I think is it nicotinamide riboside?
Yeah, we use several precursors in the salvage pathway, but yes, so we use nicotinamide riboside. So this is a precursor that is one step removed, so it makes NMN. And so the debate, Nick, as you know, is like, what is better, nicotinamide riboside? That pathway was discovered by Charles Brenner, published in Cell in 2004. Or NMN, nicotinamide mononucleoside. And that is the molecule that David Sinclair talks about. And I think the whole conversation is a big nothing burger, honestly. You can get really into the biochemistry of it all, why one might be better than another. There's some thinking that certain tissues might uptake one of the precursors better than others. I think it won't actually really matter. The reality is that some researchers or formulations will use NMN before it actually was blocked by the FDA, which we could talk about that, but because it was cheaper and easier to use. Others use NR because Chromadex has invested a lot in it, and that's where the research is, and there's good rationale that that one actually is a good one to use. I think that it won't really matter if you had a full complement of data, like all different types of studies where it was head to head. You're going to see that both have the ability to boost NAD production, and that NAD production is going to be somewhat regulated. So that is where I think the meat of the interesting story lies, is how can we boost levels so that the body has a level that is reflective of a younger amount, and then what happens over time if you continue to take it. And what I think happens is when we first start to take it, if you're older, let's say if you're like me in your mid 50s or older, 60s or 70s, your cells are going to be fairly thirsty for it. And also, I don't know if this is true, but I want you to imagine, I had this vision that just popped into my head. So imagine you've got like a downward sloping hill, and there are these big holes that are on the concrete slope, and you're pouring water down the slope, right? And all of those holes that kind of go all the way down to the beginning, the first ones are going to suck up all of the water, right, until they're full, and then the water is going to run past those to the next
Yeah.
hole. Right? Can you
I like
imagine that? Yeah.
It's a great analogy. Yeah.
Okay, good. I wasn't sure if that was going to work or not, but I loved it. I went to bed reading and I woke up and I was dreaming of this like vision. But that I think is what's happening is our cells are thirsty for this. And then once they get more saturated and satisfied, they become a little bit less sensitive to pulling it in. Now, of course, they're still using it. We talked about just the sheer amount of NAD reactions that every cell does per day, but then it can maybe make it into other tissues. So over time, the reason I think this is because if you look at the curve, if you take the same amount of, some of these precursors, let's say 300 to 500 milligrams of nicotinamide riboside, that over a month period, that the levels go up and then saturate. And if you can imagine that the reason why it's low in the beginning is not because of failed absorption, it's because of super thirsty cells that are sucking it all up. And then eventually it levels off and then maybe it's getting into more tissues. That study's not been done. This could completely be in my imagination, but as a scientist, you are allowed to sort of think about what might be going on given like the data that you see. That is entirely possible to me that, over a period of time, you're helping your body get something that it really wants. And that then would raise your physiological performance for a period of time, indefinitely. So I'd be really interested to see studies that last for years or more, and how that would, like, you have a placebo group that is otherwise matched for physical activity, diet, et cetera, and does the addition of these precursors or boosters. Does that then have, a differential effect on clinical outcomes? And I would not be surprised if absolutely the answer is yes.
Yeah. To make sure I understand your analogy fully, when you have that downward slope with a bunch of potholes in it, and say that corresponds to like different conditions or processes in the body not working as efficiently as they could, once you introduce the NAD precursor into the body, it's going to be preferentially diverted towards that area, that organ, that system, that process that needs extra support. And then once that's topped up, it might look like particular benefits such as recovery, enhanced recovery for you, or might be better cognition or energy levels for me. And that might be like the part of the reason that it translates into so many different, benefits and like potential use cases for people.
Yes. And, I definitely prefer the oral form versus the intravenous form. The intravenous form doesn't make a ton of sense to me. Yeah, there are some applications that I think you could make an argument for. But if you look at the pharmacokinetic curve of IV, you see there's 4x increase in plasma NADs. And by the way, they're putting NAD, not precursors, directly into. They can also do NR as well, and there's actually better outcomes with NR. But like you said earlier, the whole molecule cannot get into cells, so it's broken down by various enzymes. We talked about like CD38 that's actually consuming it as a substrate. And so there are conditions like alcohol, substance abuse. That's where it first became popular, like in the 70s. And there was just a couple of studies that showed that it did seem to help people who are dealing with alcohol dependence do better. That type of specific application makes sense because we're talking about extracellular levels in that extracellular activity. But in this case, what we're thinking about is, how could we get NAD into cells so that they have more energy to do their job? And giving a big bolus once a week for multiple weeks that costs thousands of dollars, I'm not cheering against it. I would just want much more specific data that shows this use case is better. And if you go to clinicaltrials.gov, I haven't been in a little while, you don't see any research. Like, people that know this space really well are not looking at IV NAD periodically. The interest is in oral bioavailability. Now, we talked about nasal forms, patches. I just don't think any of those are a better mousetrap for what we're trying to achieve. And I would need more evidence to see that it's more efficacious in certain contexts. Now, having said that, okay, go ahead.
I'm glad you brought that up because I was just talking to a group of biohackers here in Austin about that specifically, about why IV NAD doesn't seem like it's going to be the best option for general preventive health purposes. And in fact, like take that budget and allocate it on precursors and you get a more natural approach to it. Because I was looking into it and like I think neurons do have the ability to uptake NAD plus directly, but that's the only cell type in the entire body. So like that's why you see a lot of neurological benefits from IV. But the rest of your cells have to break it down, and in the extracellular matrix, the area outside of cells, when you have super high levels of the precursors like that, I believe that mimics a state called the cell danger response, which is like a negative state of like really high stress when your body's like mobilizing a lot of resources, and not something you want to do for like overall health and wellness. And it might feel great. You might have a ton of energy, but perhaps like that's not a good energy. You can skydive every day and you can get a huge burst of energy, but no one's going to argue that's really good for you and you're doing a good thing by skydiving first thing in the morning, every morning.
It's beautiful. You know, we talk a lot about oxidative stress. This is where we have these free radicals that are circulating that are causing damage to tissue. There's such a thing as reductive stress too. And you're probably driving a huge amount of reductive stress. And if you talk to people who have done an IV, it can be very painful. It's not a comfortable experience. So yes, but you did mention that there might be like a neurological application. So I just would like to see more information on that. And in the meantime, I would opt for what is much more economical to your pocketbook that has better data behind it. I think the market is way ahead of the science for IV NAD.
What about injectable NAD? Because like, it's not IV technically, but it seems to me pretty similar. Like, I don't know how the pharmacokinetics and dynamics differ from one versus the other, but I know that's another like really hot trend of these days.
Yeah, it's a higher and faster rise than IV NAD. There seems to be fewer adverse symptoms than IV. Some people say it's better tolerated. So the argument then would be, what is the purpose of faster and higher delivery? So there are actually some clinical trials underway for this in Alzheimer's disease, addiction recovery, chronic fatigue. Like I said, I would wait to see, like I am never cheering against another type of intervention that can help us. Right. If I express concerns over it, it's not that I'm a hater. It's just that I'm being sober about the state of where we are right now. So I would want to see the results of those studies. And I actually don't know the details, but ideally what you would have is a comparison arm of oral NAD over a stretch of time that would compare versus injectable. And if you saw differentiation from not only placebo, but also oral precursors, great. It's probably not what you're going to get. You're probably going to have placebo and injectable, and then you're left to wonder, well, is it better still? It's different. Is it better? I don't know.
Okay. Yeah, that makes perfect sense. I was looking at the back of the bottle and I see a lot of the ingredients are derived from a culture of S. cerevisiae. I'm butchering that pronunciation, but like, what is that and why did you guys derive a lot of the nutrients from that?
I have heard Greg talk about this. I actually forget why. So yeah,
Okay.
I think it has, oh man, what was the reason why? It's
Do you know what it
it's
is?
a natural form of vitamins. Yeah.
Yeah. Okay. Because like I see like the vitamin B6, for example, and like there's pyridoxine hydrochloride, which can be okay in small amounts, but some people get like neuropathy and other issues when they take it in high dose for long periods of time. So there's the active form P5P, and that bypasses that issue. But because it's derived naturally, I'm guessing it's not the synthetic pyridoxine hydrochloride. I'm guessing that it's a different form.
That is the one B vitamin in particular that you want to be really careful with. And so, the upper tolerable limit is 100 milligrams per day. And the dose that we provide is much less than that. It's less than a milligram. So, we're orders of magnitude away from what is a toxic level. If you were to take all of our products at once, a lot of which do contain B vitamins, you wouldn't even be close to reaching that more, that issue. A lot of the B vitamins, there is no upper tolerable limit that's been established, because they're water soluble, so you pee them out. That doesn't mean that there couldn't be issues at like super, super high doses, but I remember being a bit surprised on the podcast I did with Pankaj Kapahi at the Buck Institute. He was talking about very high dose certain vitamins, B1, B3, and B5. And so, thiamine, nicotinamide, and then pantothenic acid. And so he's using those to reduce AGEs, advanced glycation end products, which he thinks is an underappreciated element of aging. And the levels that he was using are like 8,000 times the RDI. And so, yeah, there could be some issues there with methylation. But what he's shown is actually really extraordinary outcomes. So that's pretty cool. But the one that you really do want to be very careful with, not to overconsume. I mean, I've never been a fan of more is better. So you have to show me the evidence if you're going to be using levels that are above. Now, not just the RDI, because I do think that recommended daily intakes are showing the minimal place where you don't see the appearance of near-term issues, right? That's not optimal. So, right, the amount of magnesium that we should be taking per day, according to the Institute of Medicine, is 410 milligrams for men, 320 for women. Well, there's some really cool studies that show, 550, 600 milligrams per day has differential benefits on long-term brain outcomes. And if you look at what hunter-gatherers consumed through their diets, through a variety of ethnographic studies on diet, you see levels that can be 900 to 1,400 milligrams. Those are high end, probably wouldn't be maintained throughout the year, but that's why we see people. I think that's why magnesium is having its heyday, right? Like people feel really good. There's over 600 different enzymes that are affected by magnesium. Remember, it's one of those cofactors that is necessary. It's like the bolt on the machine, right? If the bolt isn't there, the machine falls apart. It can't do its job. You need those bolts there, and magnesium is affecting a lot of different reactions. The point is that, we have these recommended daily intakes. I definitely believe that there are benefits to levels above the RDI, but that's different than megadosing. Megadosing being super, super high levels. And in those cases, I would want to see really clear, convincing evidence that that amount is better. And what I would worry about is that you would see efficacy before you would understand all the safety concerns. Like you might say, wow, we saw this improvement in cognition. I'm just arbitrarily throwing that out. But then downstream, you actually notice that you were accelerating biological aging because of X, Y, and Z. Like you don't understand the full complement of activities until you have like a lot of years of data. And we can always discover efficacy before we understand all of safety concerns. So, keep those in mind.
I don't know. Are you familiar with the orthomolecular medicine crowd? They were doing experiments with really high dose, bunch of vitamins and minerals, particularly vitamin C and the B vitamins. And I forget how much they were using. Like they're taking what are traditionally used these days in either micrograms or milligrams, and they were using like up to grams of individual B vitamins, and they didn't, like, no one died. They didn't have any major serious adverse effects in the short term. But then again, you don't really know the long term. But even then, it's like, it's still safer to megadose these than to use certain other, like if you take a caffeine dose and you do a megadose of caffeine, you do 100 times the normal dose, that's going to kill you. But like, at least the B vitamins and other vitamins tend to be safer, but still it makes sense to not go crazy with those dosages. I like that you mentioned magnesium too. You guys added a trace mineral complex into the product, which raised my eyebrows because I love trace elements in general, and it's cool to see that in the product. Why did you guys add that? And coffee berry, that's another one I haven't seen in many NAD products.
Yeah. The Aquaman magnesium, it's a cofactor for ADP dependent NAD enzymes. So when we make products, we create formulations, and instead of trying to, let's say, bludgeon a system with a super high dose of one thing, we try to look how we can complement, and in the more woo way, we say the innate wisdom of the body, but it's real. Like, how can we look at the system and understand it and then support the entire cycle for how it might be working? And in fact, what you can typically do when you do that is use lower doses of compounds. In fact, the pharmaceutical industry is tapping into this. So look at the GLP-1 craze. The new versions that are more effective aren't because they're increasing the dose of GLP-1 agonists. It's because they're complementing the formulation with other compounds that work in a complementary way to the overall end goal of appetite, suppression and lowering of body fat in a way that isn't defended against it by trying to drive up or drive down metabolic rate. And that's great, right? And that's the strategy that we've been using for a long time, is let's try to understand the system as best we can. So it's more like systems biology than just looking at a couple of studies that show this ingredient is valuable. That's where we start. Say, okay, these ingredients are interesting. Now, how do we put them together to try to get, better results? And better results can look a lot of different ways. Better results can be greater magnitude on a particular outcome. It also could be the maintenance of efficacy over longer time, or the reduction of side effects. So that's like the grounding philosophy for where we start. And so the addition of magnesium made a ton of sense, and it's the same goes for the addition of all the B vitamins. The B vitamins are, they're supporting all of the metabolic system that NAD is working in, and even the destruction pathway, so we don't overmethylate. All of those it's kind of that's how we think about it. And then for the coffee berry, the caffeine, Greg had noticed in his research, he's our chief formulator, chief product officer, that it enhances the NMN-AT. This is the rate limiting enzyme that we were speaking about earlier. And so if you have this ability to add just a little bit of caffeine, just enough where you might actually be helping that salvage pathway resynthesize NAM into NAD. So not only are we just adding more precursors, but we're also seeing if we can make the whole cycle more efficient.
Is coffee berry a polyphenol blend? Whole coffee fruit extract. So I feel like that has other benefits to it as well. And it's not a ton of caffeine. It's only 28 milligrams. So that's like what, a third, a quarter, a cup of coffee?
Yeah, it's a very weak cup of tea, right? Tea might have, 35 to 50 milligrams of caffeine in it. Now, having said that, there are different times of day that you could take NAD because of the natural cyclicity of the molecule, and you would want to support it. So you could take it in the morning, you could take it at night, and which sounds weird because we've talked a lot about energy. But remember, energy doesn't have to turn up as alertness, vigilance, or arousal. That is how we interpret it in a common parlance. But energy is just helping your body do all of its activities. So sleep used to be thought to be a quiescent state where everything rested. It turns out there are parts of the brain that are doing, and even the body, that are more active at night while sleeping than they are at any time during a 24-hour period. So what NAD at night does is to support those processes. Now, do you need to take it at night? No, you don't have to. And I wouldn't take our product at night because of the addition of the coffee berry. So the way that I take it is first thing in the morning. And that's how I do it.
Cool. I was going to ask you about that. We'll start to wind this one down because we've been going for a while. We could certainly talk forever, and I'd love to do a part 2 with you on another topic that we'll discuss later. Before we wrap this one up though, are there any use cases in particular, like situations that might make sense to use, say, an extra dose or half dose in addition to like the normal for example, if you're sleep deprived or if you're traveling or in a high like radiation or electrosmog environment, like different circumstances when you might want to consider that?
Great question. So the idea is if your lifestyle happens to collide with less than perfect, guidance. So you're traveling from Texas to France, you went out late, listened to music, which I highly recommend, go have fun with your friends. You do things that do actually tax the NAD system. Can you take more? Probably. That is what some of the smartest people in the space do, is they take a little bit extra during moments where they feel their body needs a little bit extra. So like I'll give you some examples. So it's like the sleep NAD connection. When you're dealing with sleep loss, it reduces NAD availability. And it does this by increasing oxidative stress and DNA damage, right? We talked about that already. That's going to raise PARP activity, another major consumer. And just sleep loss itself is now creating a demand on NAD. The other thing too is that chronic sleep deprivation downregulates NAMPT. That's that rate limiting enzyme in the salvage pathway, which we've talked about a couple times now. And so if you can restore sleep, that actually does help to normalize NAD levels, and for the kind of the contra reasons that we just discussed. Another major one, sleep and circadian rhythms are always talked together, but as I mentioned a few moments ago, NAD levels oscillate in a circadian rhythm. And so they're rising and falling over a 24-hour period, and they're in sync with metabolic activity, which makes complete sense, right? When your body is eating, you now have all this food to break down, and you're using NAD to then help in the metabolism of food to use that energy to fuel life's needs. So this enzyme that is the rate limiting enzyme in the salvage pathway, that is transcriptionally regulated by these two transcription factors, clock and BMAL. So it's very complex. The Nobel Prize was won on this, I think in 2017, by 3 gentlemen that were looking at the clock mechanics. But a hallmark of health is maintaining a very strong, robust circadian rhythm. And what that means is that incompatible processes are separated over a 24-hour period. Your body is not always in one state. Depending on the time of day and depending on what kind of animal you are, nocturnal, diurnal, crepuscular, your body is primed to do certain activities to help it survive. And it doesn't make, so we do a lot of repair and building up at night when we're sleeping, which makes total sense, right? You're using a lot of energy during the day. It doesn't make sense to make that into a anabolic state, right? You want to have sleep where that happens. So those are, the circadian connection to the enzymes and these levels, it ends up creating this feedback loop between metabolism and circadian rhythms. And when you disrupt that, like with shift work, social jet lag, just staying up late to chat with friends or whatever, going out, irregular sleep, these blunt those oscillations. And so you have less circadian cyclicity. So your rhythm, instead of becoming very robust, it actually flattens. And then that actually impairs the NAD cycle as well. So those are some reasons why like exercise and sleep really matter too. And I'm sorry, for sleep and circadian rhythms. And of course, exercise matters as well. Like when we're sedentary, we're not creating much of a demand to make more NAD. But when we do resistance and endurance exercise, you actually will boost the expression of that rate limiting enzyme, NAM and PT. And so that's great. Your body's going to make more. So anyway, this is a lot of detail. I hope I answered your question. But yeah, so there's a lot of factors. Sometimes we are just going to talk about the supplement. Think of the supplement as a complement to an overall lifestyle strategy. And when your lifestyle is slightly off for numerous reasons that will happen in life, you can actually take a higher dose on that particular day. And there's some reasons to do that.
Well, if you guys found this interesting, I'd love to hear from you. Go ahead and drop a comment on the video version or in the show notes. And Dr. Dan, thank you so much for joining the podcast. You guys can also check out the product Qualia NAD Plus. I have it. I love it. It's a great formula overall. I think the code URBAN would save them about 15% on their first order. So that's an option for you guys out there. Thank you for tuning in. And Dr. Dan, until next time.
Thanks so much, Nick. It was great chatting with you.
Thanks for tuning in to High Performance Longevity. If you got value today, the best way to support the show is to leave a review or share it with someone who's ready to upgrade their health span. You can find all the episodes, show notes, and resources mentioned at outlier.com. Until next time, stay energized, stay bioharmonized, and be an outlier.